Hello, can you hear me?
Yes, sir.
Okay, I've started the recording. Okay, so let us continue with our discussion of assembly language program. First of all, any questions about yesterday's topic? Quickly, if you have any question, any clarification needed regarding recursive programs and other things. You need practice, okay? Unless you practice, you won't learn it. Some practice, those of you who are in the lab, you will get through lab assignments, which is going to start from Wednesday, but like from tomorrow. But others, we need you need to practice actually. I mean, other than the lab assignments, you need to practice also, because you, as I said, you have an exam coming up on next Monday. Okay. So before that, the not much time is left. So we'll need to do that. So we will start today's discussion with instructions that can manipulate bytes, and an example of a program which works on character strings, null terminated strings, as used in C programming language. Okay. So, mostly we'll be concerned with the ASCII encoding and the classical 128 character ASCII encoding. ASCII characters usually are of 8 bits, which means 256 characters are possible. So the 128 character set is extended by adding 96 more graphic characters to have total 256 characters. That is called the Latin one. It's an extended ASCII basically. However, internationally the most popular character set is a 32-bit character set called the Unicode. And Unicode is extremely powerful. It has native support in many programming languages, including Python, and it can cover most of the world's alphabets and symbols. Okay. It allows variable length encoding, etc. So there are additional complexities. Everything is not as simple as ASCII, but we'll be concerned primarily with ASCII characters. Now, basically, we are concentrating on instructions which can manipulate one byte at a time or a half word at a time. Okay, where are this useful? String processing is a useful operation. So the byte and half word load stores are available. There are variations, two variations of the load operations. In the two variations, the one of the values, one of the variations, there is sign extension happening. Okay. What it means is that 24 other positions if you are storing a byte, or 16 other positions if you are storing a half word is through the instruction LH, and the byte storing is through the byte loading is through the instruction LB. What happens to the other positions in the register where the value is being loaded from memory? That becomes a question. So there are two options. One is you sign extend it to 32 bits, which means you look at the 8th bit, the last bit from the left, and you just replicate it 24 times more. That is sign extension. Okay. So that happens for the LB and the LH instructions. Whereas in the LBU and LHU instructions, the remaining bits are hard coded to 0. Okay, mandatorily they are hard coded to 0. And in the SB instruction, or the store byte instructions, or the store half word instructions, it just stores the rightmost byte or half word. No sign extension probably happens, or if it happens, we will just, you can just look up in the manual. Let us see an example of application of this LB type of instructions through a very naive C code string copy example. Why naive? Because this is the way probably person who is learning C programming language for the first time would write the code. It is not essential to write it so long. You can write it using pure pointer arithmetic and no iterator variable like I is required in that case. One line solution is possible, means only one statement will copy everything, extend the pointer variable and perform the necessary pointer arithmetic, everything. No explicit condition checking with equality checking with null character is required. That type of solution is possible. You can have a look at the Carnegie and Ritchie book, or maybe you already know how to do this. Anyways, we'll not be concerned with this. Essentially, I want to copy the contents of an character array y into an character array x. So x is the destination, y is the source. Very, very simple logic. And in the program, suppose we'll assume that addresses of x and y is in the registers S0 and A1, and I is in register S0. Now, if you want to perform a procedural, you want to write a procedure for this, since the iterator variable I is in $S0, which is again a very extremely surprising and stupid choice, because an iterator variable is an inherently temporary variable. Okay, why do you want to keep it in a S register? As such, there is no reason for this, but just to show you again how to save character, how to save values on the stack and later restore it, they have decided to use the S0 register to store the iterator variable I. So strcpy is the function or the procedure. Very simple logic. You have decided to use S0, so you have to first save S0, and this is not a recursive procedure, it's a leaf procedure, so just a single loop will perform the operation. You first push down the stack pointer by 4 bytes and you store the current contents of S0 on memory and save it there. Then you initialize S0 to 0. Then you run a loop called mark with L1. Okay, all the steps are, all the instructions are given with the corresponding operation shown in the comments by the right hand side. So it's very, very simple logic. Get the address of the source in T1, get the content of the current location into T2. Okay, then get the address of the destination in T3, copy T2 to that memory location and exit if 0 has been reached. Okay. Otherwise, increase the iterator by 1 byte. Remember, this is byte offset now. Okay. So all the while we'll be using byte offsets only. So I increase it by 1 and then I jump to L1. Notice that the LBU or the LB commands or the SB command, they can work with byte. Usually we have seen we increase the offsets by 4, because usually if you are dealing with things like integers, those are 4 bytes long. So one offset is 4 bytes. Here that is not the case. Here every offset is 1 byte, because this is an ASCII encoded character array. So again, you just jump to the loop, continue like this until you get a 0, until the value that you have written is 0. Notice that the comparison of the value that is being read in, whether it is 0 or not, happens after the copying has happened. What I mean by that, notice that the BEQ operation is after the SB operation, because in the destination also you need the null terminate the null character to be copied, and then you compare whether it is a null character or not. Exactly the same as the C code, same logic as the C code. After you have copied y of I, yi to xi, you basically compare the value of the entire expression xi equal to yi. You know that is the final value of that entire expression is the final value of xi. So that is compared with 0. So that logic is essentially expressed in MIPS programming language like this. Okay. Now after you are done with the loop, you need to restore S0 back to its old value from the stack. So you do that by performing a LW operation, adjust the stack pointer to go back to its where it was earlier before you entered the procedure, and then you perform jump and return, that is $array to return. Again, so from main, if you are looking at main, the function call is something like jal strcpy. With the understanding that A0 and A1 already contains the uh, base addresses of the arrays. Any question about this program? It's very, very simple, not very difficult. But still, if you have any question, please ask. Okay, no questions. Let me proceed. Now, this is an important conceptual topic which is very often needed. So you should pay attention to this. Till now, most of the constants that we have seen in say ADI type of instructions are small constants. They have a limitation that those constants cannot be more than 16 bits long. However, what happens if you require to store a value or load a register with a 32-bit constant? Okay, that's a question. Oh, by the way, one thing I forgot to mention in the previous code. Notice that for a memory to memory copying of yi to xi, you first needed to make a copy from memory to register and then again from register back to memory. So you might ask, sir, is this a very clever way of doing things? You ultimately, you know that your source is also in the memory, your destination is also in the memory. Both are character arrays inside memory. You want to copy from memory to memory, and for that you are involving a microprocessor register. Why? That is stupid. Unfortunately, MIPS does not allow any other mechanism. Okay, how will you copy? I mean, the microprocessor's domain of control is limited to the microprocessor itself. It can write values on something called a memory bus, which is shared by different other devices on your computer. That memory bus leads to the memory, and through that memory bus it can write some data to memory, and that can get written to memory for a SW instruction, or it can fetch data from memory over the memory bus for an LW instruction. But it cannot directly electronically control the memory to perform a memory to memory copy. Nothing like that happens. So unfortunately, just for a memory to memory copy, the microprocessor gets involved in the business. Why is that unfortunate? Because if the amount of data to be copied from one memory location to the other is large, it can happen. It can be very large quantity of data, say several hundreds of megabytes of data. In that case, unnecessarily you will be spending microprocessor clock cycles just to perform this copying of data from one memory location to the other. This is suboptimal. Right now we will go by this, but in future maybe we'll have the opportunity to discuss a process called direct memory access or DMA, whereby you will find that it is possible to have additional controllers to whom the microprocessor designates the task of performing this copy on behalf of itself. The microprocessor tells the DMA controller that, see, I need to copy this much of data. Usually these are contiguous blocks of data. Contiguous blocks of data, say several kilobytes or megabytes of data from this, starting from this location to that location. You take the responsibility of doing this so that I can continue to work on other important stuff. Okay. And it can perform context switch. It can designate the task to the DMA controller and it can itself go to some other business. The DMA controller on behalf of the microprocessor performs this copying, and then when the copying is done, it sends an electrical signal to the microcontroller, to the microprocessor, called an interrupt, to tell the microcontroller that it is microprocessor that it is done. So this DMA is a very useful mechanism, and not only the microprocessor, it can perform memory data copying for many other devices also. Another common example is that suppose you want to somehow save some values from memory to your, say, USB drive or something, or from USB drive you want to put it in some other device. So this sort of direct copying, it need not involve the microprocessor directly. It can be handled by other controllers on its behalf. So then that is what is done usually in practice. Anyways, coming back to how to initialize registers with 32-bit constants. For a 32-bit constant, the MIPS instruction set has a peculiar instruction called load upper immediate, or LUI. Load upper immediate is not, it has got nothing to do with unsigned. Okay, don't confuse LU with uh, unsigned. Why is this peculiar? Because this is a 16-bit constant. Can you, it copy the side, that is the MSB. For example, if you execute the expansion of 61 is this. Sorry. Whatever is highlighted here. Okay. That gets and stored on the left hand side, on the MSB side. So this is slightly peculiar. LB instructions or LBU instructions do not work like this. They copy on the LSB side, but this guy copies on the MSB side. Why did it copy on the MSB side? The goal of this programmer is to have this final, this 32-bit value shown here in this final box. He wanted to store this value. Okay. So he calculated what are the binary representations of this. He broke up the value into two parts. One part is the MSB side, whose encoding he saw is 61. And he loaded, he used LUI to fix the MSB side to with that 16 bits. And the LUI instruction also forcibly clears the right half to all bit 0. Also an additional property. So all the remaining 16 bits starting side up to the LSB is cleared to all bits 0. Once that is done, done because you want to express this 0000. I mean this binary string 00001001 00000000. That is 2304. So that you use to basically odd, and that gets odd with all bit 0. So overall effect is that the entire thing highlighted value gets stored into register S0. Okay, any question about this roundabout way of storing? This is conceptually important. Okay, that you do not understand. Fine. Now we'll come to another important topic, which is kind of the final topic of our discussion. It is the different addressing modes. The word addressing mode is slightly confusing because it has more wider sense than what you mean by memory addresses. The word addressing mode in the context of an instruction set architecture basically means all the ways instructions can be written, all the ways in which instructions can access operand values. Those values can either be in registers or they can be in memory locations, in main memory locations, anywhere. Okay. How are these values accessed? The collection of all these mechanisms are called the addressing modes that are supported by that instruction set architecture. Okay. Now, what we will study now is till now we have been dealing with this type of branch instructions like BEQ, jump instructions like J, and every time we have been working with text labels like L1, L2, etc. But these text labels as such is very convenient for writing programs, no doubt, but they do not have any real significance because eventually you need memory addresses which will be stored inside instructions. So the J instruction encoding would also have 32 bits with some value shown to tell it where to jump to for corresponding to that level. Now we'll study the way in which the assembler figures out these numerical address values, okay, and how are these computed. So again, this is slightly peculiar. It's not very straightforward. So please pay attention. Let us consider instructions like branch, say BEQ. What is a BEQ instruction? Just to recall, it contains, say, two registers are compared. One label is mentioned. This label is, what is the encoding of this label is not clear. That is what we are going to figure out. Okay, so there is an opcode. This will probably opcode will be encoded in 6 bits. These two registers will take up 5 bit, 10 bits together. So 6 plus 10, 16 bits gone. You have 16 bits in your hand to somehow designate this label L2. What can you do? One general observation is that most branch targets are near the branch instruction. So if you look at the BEQ instruction here, where was it branching if these two are equal, these two registers are equal? It was branching to register L2, which is at a distance of only 3 instructions from it, right? And the difference between this end of this instruction and the start of this instruction is only 8 bytes because this instruction is 4 byte, this instruction is 4 byte. They will occupy 4 byte each in memory. So you only need to jump 8 bytes. That's not much. Okay. So actually most of the times in most of the programs, the branches are relatively nearby, not too far away. Either within say 20-30 bytes in front or 20-30 bytes at the back, something like that. Not 20-30 bytes, but definitely within say 100 bytes on the front, 100 bytes on the left, something like that. Now, the constant that is mentioned in the 16-bit is a signed constant. If it is plus, then it can branch forward. If it is minus, it goes back. Okay, so both forward and backward branches are possible. The constant will be encoded in 16-bit 2's complement system. It saves some bit out of the 16 bits. It gives a 16-bit constant, but then it multiplies by 4 when the actual address to which branching should happen is calculated. It sees the current value of PC, that is the program counter. What is the current value of PC? Suppose this BQ instruction is at address 100 in decimal. What is the current value of PC, students? Any of you? What is the current value of the program counter? We mentioned this in class earlier.
104.
Good, very good. So because the program count, it was also mentioned on the slide, the program counter points to the exact next instruction that is going to be executed in sequence. Unless branching happens, by default, everything sequential execution happens. So by default, it is pointing to this instruction, whose starting address is 104. Why 104? Because if the starting address of this instruction is 100, every instruction is 4 bytes. This should be 104. Very good. So currently, so it looks at the current PC value, and the target address is the whatever offset this 16 bit is mentioned, then multiplied by 4. Why multiplied by 4? It's an observation that since the instructions are okay, so the example is this. So this is a valid instruction address encoding. So one instruction can be in these are decimal notation addresses. 80,000, then it can be 80,004, 80,008, 80,012, 80,016. This is guaranteed because of the regularity of length of MIPS 32 instructions. So with this clever observation, it says fine, okay, so 2 bits I can save. Don't worry about mentioning these 2 bits and waste 2 bits of space in this 16-bit offset. I will not mention it now. But the hardware, when it calculates the actual address, it takes the current PC value, takes the offset and multiplies 4 with it to calculate the final jump location. Now that the fact that PC is already incremented by 4 when this calculation is taking place, that is taken into consideration and corrected by the hardware. So the actual calculation that is performed, we will see very soon what it does. The address translation hardware. This mode of addressing, where you calculate addresses with respect to the program counter, okay, is called a program counter relative addressing or PC relative addressing. In general, if addresses are calculated with respect to the content of any register, this is a relative addressing. The most common mode of addressing in MIPS is this relative addressing mode. Okay. One thing you should notice is that when we were writing the BQ instruction, there was no mention of program counter or anything. That is not evident what is program counter, what role is it playing in calculating the final address to which this branching should happen. Nothing is evident. Everything is hidden from the programmer to make his life simple. The programmer can simply write the program using text labels like L2, and the assembler takes all the trouble of converting these things into the actual addresses. Okay. That where when it finally stores the assembles and creates the binary executable, it takes all the trouble of these internal address translation mechanisms and does all the calculations and encodes B Q correctly. This are absolute jump addresses, jump addresses. So the two instructions that we have seen which can perform absolute jump addressing are J and JAL instructions, right? We have seen that. JAL is very similar to J. The only additional operation JAL performs is it copies the program counter content, which is the next instructions which was supposed to be executed if everything had happened serially and no function call would have taken place, then things would have been in sequence. It copies, and that is currently in your program counter. So that value it just copies into the return address register $RA. That is the only additional operation it performs before it allows the jumping. But jumping to what location, that address has to be calculated. The calculated address is a 16-bit number, but again to save 2 bits, you it only mentions something, an offset, which is then left shifted by 2 positions, that is multiplied by 4 and concatenated with the upper 4 bits of the program counter. Again, this is kind of an address calculation with respect to the program counter. Why the program counter is currently at some value, okay, and I only have ability to jump in front or the respect value. So I take part of the program counter in 28 calculate 6 and left shifting into 2 positions. Okay, nobody multiplies anything by 4. It is left shifted by 2 positions. Okay, and that then it is just concatenated with PC to obtain the overall address. This is called a pseudo direct jump addressing. Why pseudo direct? Well, it looks like direct jumps, but again in the background behind the scene, program counter is actually playing a role. Okay, it's not the only the address. If you take the 26 bits and multiply it by 4, you will not get the actual address where jump will happen. The jump will happen to an address. Get that entire address, you also need information about the MSB 4 bits of the program counter. This is it looks like a direct address jump address, but it is not. It's called a pseudo direct jump address. Now this example on slide number 53 is very important. Okay, addressing in NIPS. Let's see. So this is an code from some earlier example. There is a loop body, a very simple loop, a 6 instruction loop body. It has 2 types of branch and jump instructions, a BNE instruction and a J instruction. So it shows opcode, then the 2 operand, 2 register operand values, numerical values, and then the other fields. Okay, so SLL is shown. uh, add is shown. We have seen these things earlier also.
Oh, sir, I had a question before this.
Yes.
What really happens to the program counter in a jump instruction or when?
Okay, good question. Okay, I should have described it earlier. Later, when we study the actual MIPS hardware, you will find that the program counter is an internal register which gets loaded with the starting address of the program. Uh, this is usually when you invoke the program from the address hard instructions, portion of memory called the level of memory between the main memory and your microprocessor. It fetches instructions from the instruction cache into the internal registers and starts executing. And automatically every clock cycle, as soon as it fetches an instruction from a memory location, it increments by 4. So for example, in the slide that is opened here, it fetches the instruction SLL $T1 $S32, the encoding of this in 32 bits from a particular memory location 80,000, whose address is 80,000. After fetching this instruction, immediately in the same clock cycle, it increases its content, increases the next it to 80,004. So that in the beginning of the next clock cycle, it can fetch the instruction from address number 80,004. This increment by 4 is automatic and the default behavior. The problem happens when, say for example, in the BNE instruction, when it is executing the BNE instruction, it has fetched the BNE instruction from memory location 80,012. Already the program counter has itself uh, is waiting to fetch instruction 80,016 in the next clock cycle. However, if the branch not equal, this condition succeeds, that is the register contents are unequal, then it suddenly branches to a location exit which is 80,024 and not 80,016, which means not in sequence. There, by force, the PC address is overwritten, okay, so that in the next clock cycle, the actual execution can start happening at 80,024. But as I said, I think in the lectures earlier, I said the processors are designed to operate sequentially. They get into trouble.
So your voice is cracking a lot.
Happen. Default memory counter that it is kind of. Hello, can you hear me? Hello. Hello, students. Can you hear me?
Yes, sir, I can hear you now.
Okay, so it gets into trouble if this sequential execution does not happen, because then the correction needs to take place. Okay, so because we are not showing the clock cycle based execution here, you are not getting the complete picture. Every instruction ideally takes one clock cycle to execute, and before the next instruction executes, the processor by default greedily it assumes that exactly the next instruction in sequence will get executed. Just a moment, just call. Hello. Okay. Uh, So that is the default behavior many times is not the correct behavior, and that time problems happen. What type of problems happen and how to solve them, we will discuss when the time comes, when pipelining is covered. Till now, assume that just kind of keep your eyes closed so that there will be no issues. And program counter value will be modified, and then execution will continue. But suddenly trying to modify a program counter value, especially if you have a pipelined processor, that is problematic. Why problematic? Again, that unless you see the structure of the pipeline and you analyze the structure and you analyze how it works, it is going to be difficult. Hello, madam, I'm class A. I will call you after 12. Okay? Okay, so is that clear, student? I know it's not the complete answer of what the program counter does. Program counter contains the address of the next instruction that is going to be executed. The computer hardware reads the program counter to get the address of the next instruction and fetches that. Okay, tries to make sense of it, what it is. It makes sense by reading the opcode. Then if the opcode is valid, it understands, okay, this is an add operation, fine. Let me read the register fields, figure out what are the operands, then maybe immediate fields, etc, etc, etc. Okay, this process of reading in, after reading in an instruction from memory is called instruction fetch. Trying to make sense of what 32-bit thing has been fetched inside is called instruction decode. Trying to decode what this 32-bit string means. This is called fetch, decode, and finally execute what the instruction wants you to execute. Instruction means it is asking the microprocessor to do something, right? It is instructing. It is giving an order. And trying to obey this order is called execution of the instruction. It is called instruction execute. So fetch, decode, and execute, this operation keeps on happening again and again and again every clock cycle. Okay, this is a fascinating topic. Many complications exist. When time comes, be patient. Later half part of the course, we will go through these things in detail. Fine. So suppose the binary encoding of SLL is shown there in the boxes 0019940. It has 6 fields. Similarly, add instruction also has 6 fields. In decimal, those values are shown, etc. Notice at the BNE instruction, question is, what should the BNE offset field be? First of all, BNE offset field, it needs to jump at location exit. Exit, it's at a distance 12 bytes. Okay. But when the offset is going to be calculated, the program counter is already at a value 80016, and that is taken into account. Okay. That is taken into account, and the offset is stored as 2. Why? Because if you add 80016 with 2 multiplied by 4, that is 2 shifted by 2 positions to the left becomes 8. You obtain exactly 80024. That's why the offset stored here is 2 and not 3. It should have been 3, because 3 multiplied by 4 is 12, and then it says that, okay, I need to go to 80012 to 80024. But no, it is 2, because by that time the PC is pointing here. Okay. And if you look at the address calculation scheme, it is current value of PC plus offset multiplied by 4. So the offset field must be 2. Okay. So then look at jump loop. Okay, jump loop, what it does, how does the jump instruction calculate address? It takes the 4 bytes from the PC and it has the address multiplied by 4. Whatever offset will be mentioned here, that will be multiplied by 4 to give the final this thing. 80,000 is a number which does not need 28 bits. Does it need 28 bits? I don't know. At least 20,000 is a number which does not need so many bits. So it takes 20,000 multiplied by 4 to get exactly 80,000. And the remain these 4 bits on the MSB side of PC does not create any problem because these are very close by. So the 4 bits of the PC are expected to be the same. However, in spite of saving 2 bits by this clever observation that last 2 bits will always be 0, 0, so I do not need to mention them in the offset, in effect saving 2 bits, even that is sometimes not sufficient if you want to jump very, very far away in your program. Suppose your program is extremely long and suppose the assembler sees an instruction BQ $S0 $S1 L1. The problem with the L1 type text labels is, see, the user doesn't care how far the branch target address is, whether it can be encoded in 16 bits, it cares about nothing. He just writes text level L1 and writes another that describes that level later on somewhere. Question is, the assembler has this headache that whatever he has written, that has to be translated so that the BQ functionality is exactly implemented. However, if 16-bit offset is not enough, even after this multiplication by 4, it is not enough. The program is so large. In that case, it looks at the label and transforms them into a collection of 2 consecutive instructions. It says BNE L2. It just transforms them slightly differently. It transforms it into a collection of BNE followed by a J instruction. Why a J instruction? Because the J instruction would give you 28 bits, 26 bits actually, and 2 bits for free. So the jump instruction will give you 2 bits for free, and the very next instruction after jump it labels as L2. Okay, so basically here whatever was there after this very BQ instruction, that is marked as L2. If the registers are not equal, it goes to L2. Otherwise, it makes a direct jump to L1. In that way, it expands the possible number of offsets to branch to a far away location at a location for which 16 bits are insufficient. So the summary of the addressing mode of the MIPS are this. There are only 5 addressing modes, of which the first one are immediate and register addressing modes. They don't even as such involve any addresses, any memory addresses. They just deal with registers, but still they are called addressing modes because they show how operands can be mentioned in instruction encoding. Okay, so one is an immediate addressing mode, one is a registered addressing mode, most simple. Then is a base addressing mode that is used for LW, SW, LB, LBU, this type of instructions, SB, SBU, SB, etc., SB, SH, LB, LH, etc., all these instructions. That's the base addressing mode. Then the PC relative addressing mode is used by the branch instructions BNE and BQ. And finally, the pseudo direct addressing mode is used by the jump and JL instructions, J and JL instructions. There are only 5 addressing modes. The number of addressing modes at this stage, it might seem to you, oh, it's too complicated. I mean, come on. I mean, this is 5 addressing modes in one instruction set. Believe me, this is a very, very less number of addressing modes. There can be instruction sets, for example, x86, 64, which support dozens of addressing modes. For example, there might be an instruction which says read a value from memory address this, read another value from memory address this, add them and store into another memory address this. So an arithmetic instruction itself supports 3 memory addresses. There is nothing like that in MIPS. Arithmetic instructions will either be immediate or will be pure register. Okay. In x86-64 also, your those instructions, those values will first be fetched from memory inside internal registers. Addition will be performed and then it will be stored back into the memory. Anyway, that will happen. Okay, but it allows programmers to write things briefly by having less number of complicated instructions, which lets you write things in a very sophisticated manner. However, does it improve performance? That is difficult to say, because internally, eventually, those hardware series of simple RISC type instructions, okay, like LWSW type instructions, which do the work exactly like we have seen happening in MIPS, that you first get values from memory, operate on them, and then store them back into memory. Okay, there is no way that direct addition can take into can happen in memory. Okay, DRAM chip is not a magical thing that you can directly go inside it, perform an addition, and take the value and store into another DRAM location. That does not happen. Addition operation needs circuits. Where are the circuits in a DRAM chip? Those circuits are present only in the microprocessor, so you must fetch the values anyways. Okay, so the one of the characteristic features of a RISC instruction set, maybe this was taught to you when Professor Bhattacharya taught you, the number of addressing modes that is supported in RISC instruction sets, like say MIPS 32, is less compared to the number of addressing modes supported in CISC instruction sets. Okay, what is the difficulty of supporting less number of addressing modes in the CISC instruction set? Well, the difficulty is your hardware becomes extremely complicated, because the hardware needs to kind of handle so many different types of addressing modes. Okay, whereas in the MIPS or RISC machines, the hardware itself relatively is less complicated. Okay. Then there is a bubble sort example using a swap procedure, and the swap procedure is a leaf procedure. I won't go into the details of this because you can understand this. It's not difficult. Again, it's basically it's just performs a procedure. At the end, there is a JR instruction. Okay, and the sort procedure is a non-leaf procedure because it calls the swap function. So again, it shows. I mean, it might look bombastic, but it's not a very difficult because it is highly commented, nicely commented piece of code. It is not very difficult. It is also not a recursive function. There is a double loop. That's why it looks scary. I think this for loop, second for loop has been, I mean, it's kind of complicated looking, but yeah, I mean, you know, bubble sort is not a particularly complicated algorithm anyways. So it shows the full procedure, so you can have a look at it. Fine. This we have already discussed what happens. Please note that the SPIM software that you are going to use is not an assembler as such. It is a simulator. It is a simulator of an assembler. Okay, it doesn't really generate any binary in the MIPS instruction set. Maybe you already know that compilers which run on one type of instruction set on computers with say x86 processors and can generate code targeting other types of processors are called cross compilers. For example, GCC cross compilers probably are available for MIPS 32, etc. Or ARM targeting the ARM instruction set, but they will execute on your computer. Okay, but the binary that they will generate will be you can use it for other type of processes. I I don't remember whether I mentioned this. I'm just writing it so that if you want to generate directly assembly language programs, you can say you can give a flag. I think GCC, then you can type minus capital S. Let's say something hello.c. This is going to generate a file hello.s. This assembly language file this hello.s file, this thing, this .s is a text file which you can open and of course it still has some segments which will etc. But of course the instruction just as an interesting example. Now, what are pseudo instructions? We have already discussed this. These are things that the assembler comes up with and supports. What pseudo instructions are supported by the spin simulator? You have to look at the manual. I know it supports move. I know it supports BLT, although we have discussed there is nothing called BLT in the direct branch on less than. It is not supported directly in hardware. All of these will be expanded into their equivalent forms. In fact, if you write programs using pseudo instructions and load them into spin, you will find that when that program has been stored in, I mean, the memory encoding is shown, it will be shown with the actual instructions. For example, if you have written some move sorry, I went offline for some time. Hello, are you there?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So, how does a program gets loaded into? Okay, so yeah, coming back to pseudo instructions. In your exams and lab assignments, you will be provided clear instructions on whether you should use pseudo instructions or not. If nothing is mentioned, you are free to use pseudo instructions. Okay. But if it is imposed that please do not use pseudo instructions, then do not use it. Okay, but if nothing is mentioned, stage, etc. I won't go into all this systems in detail in the next course. Point going into these things right now because we give you a complete picture. So much stuff has to be covered. It is not possible. Create virtual address space. How I mean come on. I mean that is very difficult. That's a critical topic to cover right now. But anyways, we don't need to bother too much about it. Finally, you'll study this thing. So moral of the story is that powerful instructions are good. Fewer instructions are required. You can write your code. But complex instructions are hard to implement in hardware and may slow down all instructions, including the simple ones. Why? Because your clock frequency is constant. You cannot say some instructions are slow, so it will run at 500 megahertz. Some instructions are fast, then clock will run at 1 gigahertz. No, that is not possible. Okay, the clock of your processor usually is constant. Nowadays, such that the hardware is going to result to will be efficient. So this is a constant exercise of what should I say, cooperation between the instruction set designer and the circuit designer. These two people must talk with each other. If the instruction set designer says, see, I have designed an extremely fancy, very clever instruction that can do a magic. But the circuit designer says, okay, fine, I can design a circuit for it, but it will only run at 100 megahertz. And you want your microprocessor to run at 3 gigahertz. It is not possible. So that will not become part of the hardware. Okay. So these people must talk with each other. Both of their roles are important. The instruction set, what instructions will be supported, is an extremely important decision for a microprocessor. Similarly, what circuits the microprocessor is going to have is also a very, very important decision and requires a lot of skill to design very fast circuits. For example, you have 4 gigahertz your clock speeds in modern microprocessors. Okay, they intentionally run it at slightly less clock frequency. Like if something is rated to run at 4 gigahertz, it could have run at 5 gigahertz probably. Okay, can you imagine 5 gigahertz clock frequency? 5 gigahertz is 0.2 nanosecond. In 0.2 nanosecond, one instruction has to be executed and the hardware circuits inside it will execute it. Later, when you study arithmetic functions, multiplications, divisions, etc., you will find these are difficult things to do. I mean, performing a 64-bit multiplication in one clock cycle is a non-trivial thing. But circuits do it for integer multiplication. For floating point multiplication, okay, multiple clock cycles might be required. For floating point division, as many as 40 clock cycles might be required. Okay, because the algorithms are sequential, it's not a single iteration algorithm, multiple iterations are required. Okay, but still, I mean, the circuits are mind-bogglingly fast. If you design such a circuit in the FPGA or in the lab, or even if you do using VLSI CAD tools, you will never be able to design such fast. None of us will be able to design such fast circuits because these companies have extremely skilled circuit designers who can design those fast circuits using techniques that they are kind of in-house and kind of very cutting edge. The textbook circuits will never run at that frequency. Okay. So compilers are very good and they are becoming better over the years at making generating fast code from simple instructions. Okay. If you give the simple instructions to the compilers, they are very good at arranging them and translating the code from high level to a series of code to a series of simple instructions, which will execute quite nicely. Okay, so more lines of code does not necessarily mean less. Better. I'm sorry. So, will you use assembly language programming? That is a question. Well, for high performance yes, compilers have become so good, it is difficult for a human being, however skillful in writing assembly language, to beat the performance of a compiler generated program. Okay, so people, the use of assembly language programming directly, other than maybe writing some very low level code, maybe which deals partly with the, say, the ROM type of things, or the bootloader, this type of things, when the operating system is getting invoked, or maybe some device driver type of things, some interface code between hardware and operating system. Other than this type of things, it has become almost directly nobody writes operating system code, and even if they write operating system code, oh, my voice is breaking. Okay, there is not much again. The internet connection is I'm sorry, but again, it's not much I can do. Uh, Hello. Yeah. So maybe you can look at the recording later on, and maybe there it will be better. So direct assembly language programming is done by very few people nowadays. People depend on compilers to generate high level code. Some small part of the Linux kernel is still assembly language program, I believe, but very small part. And most people use only direct high level language coding and depend on good compilers to translate it to good assembly language programs. And other than that, what can I say? Uh, well, one unfortunate thing that has been observed is that people have tried to study how much productive assembly language programming is, and unfortunately it has been found out that the number of lines of code written in high level programming language and in assembly language, if you consider one instruction to be one line of code and along with combined with comments, etc., is approximately the same by skillful programmers. Which means if a skillful programmer writes 500 lines of C++ code in one day, correct C++ code, and skillful assembly language programmer will also write 500 lines of assembly language code in a day. But 500 lines of assembly language code probably corresponds to 25 lines of C++ code. So if you compare the productivity in that way in terms of high level language lines of code, productivity of assembly language programmers is much less on average. Okay, and that is very unfortunate. It takes much more time to debug. The debugging tools are not that good if you are dealing with writing direct assembly language programs, whereas the debugging tools for high level programming is very good. The IDE support for assembly language programming, it is there, but not too much. So also is not these are things which ultimately make discourage people from writing assembly language programs directly. Okay, but for this course it was necessary for you to learn exactly what keeps on happening in the background. So we have covered this topic. We'll solve some assignments in class, but later on in life, whether ever you are going to write assembly language code, I'm not sure how many of you are going to write, but nevertheless it is a useful skill to have, to understand what keeps on happening in the background, because the computer understands only binary programs, and to understand instructions in binary format, the intermediate form, that is between high level and binary, the assembly language is a very important intermediate form. Okay, so thank you. I will give you Thursday to be, if you agree, I can give you Thursday to be a study leave, or we can be present on Thursday for doubt clearing. Okay, so let us do Thursday, let us be present for doubt clearing. Practice some programs, look at the textbook examples, look at the examples in the slides, try to use the Steam simulator to write some programs, and those will be assigned to you tomorrow also. Okay, and best of luck for your exam on Monday. Okay, thank you very much. We will meet on Thursday for doubt clearing.
Thank you, sir.
Thank you. I'm stopping the recording now.